I haven't opened up yet, but the pen charging options are a lot easier. So here we have an array of vertices. For each vert, a linked list of adjacent vertices. And I'd say this is a fairly common way to do it. So, oops, I'll decline that phone call. Okay. And here we have vertices. We have a matrix, right? Indexed both by vertices, and this is a 1. We get this element is a 1. We'll call this the ij element. If vi to vj is an edge, 0 otherwise. Okay, and the nice thing here is you can change that to weights of the edges or something else like that. And you can see that a lot of these axes are a constant time. But this space is kind of what the trade-off is, and v squared space could be quite a bit of space. All right. Are there any particular questions about this table or anything surprising you see? I'll give you a minute to look it over. So the book goes into more detail about this, and it walks through what the data structures are a little bit more. So if you're uncomfortable with using either of these data structures or any of these, I would take a closer look. Actually, this fast adjacency list is using this hash tables instead of the linked list. This is, we'll say, a spin-off. Oops, spin should only have one off. I wonder if my arrow should go the other way, but that works too. Okay, so the hash tables are kind of very similar to the first data structure that he describes. And this kind of goes to something else too, is that, not only is there more than one way to answer a problem, there's more than one data structure you can use to answer a problem. And you have to try to figure out what the trade-offs are between one approach versus another approach, right? So for some things, like the adjacency matrix might be more convenient. For example, you can think about, there's something called eigenvalue decompositions of graphs, and that gives you certain information. So maybe you like this matrix form because it's easier to do some linear algebra with. If your graph is pretty dense, then, and if v plus e then is about v squared, then you might as well just use the matrix, and so forth. So let's see here. Oops. Okay. Lecture part 2. Yeah. So the book, so there's 2 chapters right now on the graph data structures. There's chapter 5, which basically we've kind of just went through between earlier today and yesterday, or 2 days ago. And there's chapter 6. Chapter 6 focuses on depth first search. Now 5 also went through whatever first search and goes into more details of depth first search. But then it goes into some algorithms that use depth first search, including topological sort, which we've discussed before. But I wanted to kind of look into the strong connectivity as another algorithm to think about. So let's give you a definition first. Okay, so the connected components of a graph. So if G is a graph, we'll say undirected. The connected components of G are essentially a partition of the vertices, right, into vertices that can reach each other. Is a partition of the vertices into sets such that, I guess I don't need to say into sets, so a partition of the vertices such that V and W in my vertex set are in the same partition if and only if V there exists a path from V to W. And if there's a path from V to W, we can reverse it and we can say, and hence a path from W to V. So we'll give an example. Is if we have some kind of a graph, right? And it doesn't really matter if we have things. Right. And the partitions are exactly what we would think about them as. And so I'll put them in. I'll circle. There's component 1. There's component 2. And I made this hard on myself, but it's more fun. This is component 3. And that's component 4. And you can see, I'll just choose one of them. Here we go. Component 4 looks like this. Right, and here's V, here's W. I can go V to X, X to W, and I can go backward to get from W to V as well. But there's a way. Now I can't get, say, V, W, X, we'll call this Y, right? There's no way to get from V to Y, okay? And there's a little bit to be proven that this is a partition of them, but it is. Doesn't work so well on directed graphs. Okay, so for example, if I have, we'll just make it 5. Okay, if this is V and this is W, and oh, I should make things directed. Okay, now in this case here, I can go from V to W, and I can get from W to V, right? That's nice and well defined. But in this other case, if this is V and this is W, right? V can get to W, but W can't get to V. Okay, so this partition is not exactly well defined then. So we make another definition. A strongly connected component. Of a directed graph is a partition of the vertices into, sorry, I want to say what they're into, but such that B and W are in the same partition. If and only if they are mutually reachable. Okay, so this kind of one-sided condition, it works with the directed graphs because we can kind of go backwards, but not with the undirected graphs. Now let's see what this would kind of look like, and I'll make it a little bit easier for me to draw the circles around things. Okay. I'm gonna okay. So we can do another one too. Okay. And if I label these A, D, E, F, who can explain to me at least one of the strongly connected components?
A and D are in a strongly connected component.
Okay, and why is that?
Because you can get to A from D and to D from A, but you can't get to
I'm enjoying the mixed light.
A and D from any other point.
Right, yeah. So we can get to A and D to each other, and we can get out of those two, but once we get out of those, away from those two, we can't get back. Okay, what's another strongly connected component here?
E, and F.
Okay, oh yeah, I lost my F, didn't I? And why is that?
Because at any one, you can just kind of cycle around and get to another.
Mm-hmm. Yeah, and then we notice that, well, edges going into it aren't able to, like, any edge coming into it. So from A and D, there's no way to get to A or D, and any edge going out of it, we can't get back if we go out. Okay, and then the last strongly connected component is the C. Okay, and we can take these things that we just created there. So we have this one corresponding to C is green. Oops. This node corresponding to B, E, F, and another one corresponding to A, D. And I can create another graph here where my nodes are just my strongly connected components. And this graph is called the meta graph. I'll say nodes are the strongly connected components. Edge, if can get between them, we'll just say. Okay, and you could imagine that this is one way of kind of taking a big graph and condensing it down to make it something smaller, easier to work with. But the question is, how do we get this, right? So this is a question. How do we compute this? Let's first think about Q1. We can first think about, can we figure out what the strongly connected component of a graph, of a vertex is, right? Given little v in V, how can we find the, we'll call it S, strongly connected component of V, defined to be the strongly connected component containing V? Does anyone have a guess of how we would approach this?
I guess we could do a depth first search, or well, really any kind of search from V, and then mark all the nodes that V can get to, and then do another search starting at each of those nodes and see if they can get to V.
Yes, so let's do this here. So we are in the depth first search section, so this is the strong hint of how we should do it, right? So let's do depth first search starting at V. And find all vertices that are reachable from V. Okay. And what is this time complexity of doing a depth first search?
It's big O of like V plus E, right?
Mm-hmm. Yeah. So the number of vertices plus the number of edges. I'm going to leave it as big O because we're actually going to come back to that. So now I know everything reachable. I need to know if I can get back. So we'll say pass 1. And we'll call this set reach of V. For each W in reach of V, do a depth first search and check to see to find V, right? And so this would be a second depth first search for every one of these. So the total time. And so let me just give a shortcut here. So we're going to say N is the size of V, M is the size of E, just so I can make this a little bit easier. Right, is going to be, again, N plus M per vertex in there. So this is now going to be O of N times N plus M. Okay. So this is fun, right? Right, and m can be O of n squared. So this is, at worst, O of n cubed. Okay, and I think a lot of time, especially if you take a complexity analysis class, is to, well, once we have a polynomial algorithm, we're good. But even with n cubed algorithms, this can take a long time. It might not be the best. So the other option, I guess I can put this here too. There's 2. Would be to reverse all edges and do depth first search from V. I guess we can call this reverse depth first search in case we ever need it again. Okay, and then take the intersection of reach of V. We'll call this set reverse reach of V. Reach of V, intersect reverse reach of V. Now, okay, now it's going to depend on, do we have a nice way to store them? But at best, combining these two and taking this intersection is going to be linear, right? And because we have to look at everything. Right, I can think of, okay, maybe we sort them first and then do a linear thing. So we'll say at best, this is linear. Okay, but it might be n log n. I mean, if we would need to sort things first. But so this is essentially, even if we can do this linear time, now to do this for every vertex, right, we get theta of n squared plus n. But we'll just not do this. We'll assume that we can get this in the linear time. Yeah, but however, we can do this in linear time. Okay, and maybe I will give you the idea of it, right? So if I were, so I look at this meta graph, right? And I'll say lemma. The meta graph is a DAG. Oops. Does anyone have a quick proof of this?
Sorry, what's a DAG?
Directed acyclic graph.
Lesson learned.
If it's not a directed acyclic graph, then it would be a directed cyclic graph, and that would mean that you can get from one strongly connected component to another strongly connected component back to itself, so they would be part of the same strongly connected component.
Yeah, so their proof goes by contradiction. Assume there is a cycle, then can get from then let's say there exists components, like strongly connected components, C1 and C2, such that there exists a path from C1 to C2 and from C2 to C1, right? Let V be in C1 and W in C2. That implies there exists a path from V to C1 and a path, V to W and a path from W to V, which means V and W are in the same strongly connected component, which is a contradiction, right? Because we assume that we started with our strongly connected components. Now there is, I'll put this here, a few details here. To be worked out, but I'll leave that as an exercise for you to just think about. So we're at the end of our time, and I will, I guess, look forward to some messages from you on Piazza today, and I'll chat with you all later.
Can I ask about the homework real quick?
Yeah.
I guess it's problem 2 and 3. It just says chapter 4, question 1, greedy schedule, for example. Is that we're doing all pieces of that problem as stated in the textbook, or are we doing like more like a presentation of the greedy algorithm with like a proof of termination and a proof of partial correctness, or?
Yeah, so, well, problem 4, question 1 and 3, right? So 3 is to describe and analyze an algorithm. So if you're asked to describe and analyze, you need to do all of the pieces of it, right? Question 1 is more specific. So it's more like a proof.
So do we have to prove all of those 9 different possible algorithms?
Well, you either prove that the resulting algorithm chooses an optimal schedule, or describe an example that contradicts it.
Okay.
So they won't all be, I guess they won't all be proving correctness of it, but.
Okay, perfect. I think I'm just going to throw this out there. I think that and I imagine others would agree, we'll need more than just till Monday on this.
Yeah, I'll push it to Thursday.
Okay. I'm like honestly even a little concerned that Thursday would be enough time, just to be totally honest about it. Knowing how long these can take. But definitely by Monday, you know, especially given the Piazza caveat, you would need to start making posts, like 4 posts today, right? The number of contributions that can count from a single day are the number of days before the assignment is due plus 1.
Yeah, because I didn't want everything on the last day again.
Yeah, no, and I agree. Fully. Yeah. That's just my initial 2 cents after kind of looking through it.
Okay. Yeah, I'll extend it till Thursday and then we'll take it from there. But I think, yeah, and you're welcome to use Piazza to discuss even questions 1 and 3. So,
Okay.
Mhm.
Thank you.